despite the greater uncertainty inherent to more deeply unprecedented scenarios, there are questions we still have no choice but to tackle. For example, governments and universities need to set their policies for oversight of dual-use research of concern. If they want to introduce regulation or oversight over influenza research, for example, they need to balance the potential benefits and harms this could cause. On the one side, certain regulations could prevent risks such as the intentional synthesis and dissemination of a pandemic influenza virus. On the other, they may hinder research that can assist in developing medical countermeasures for existing or naturally arising influenza. We mentioned the Johns Hopkins and NTI estimates for the harm of a bioengineered attack. Let's now develop our own complementary estimate for how many people we expect to try and perpetrate such an attack in the upcoming decade. When confronted with a question we have no direct data for, or even worse, we don't really know how to begin to estimate, we should recognize we're unlikely to get an extremely accurate answer. But often, a rough answer is enough, just getting the order of magnitude, the general scale of the answer, right. If the answer is around, let's say, 10 people this decade, our policies should be very different than if we expect 0.1 people. That is, only a 10% chance that one person does this decade. When all we need is an order of magnitude, a useful tool is Fermi estimation, named after the physicist Enrico Fermi. In this method, we break down a hard-to-estimate question into multiple factors that are easy, or at least easier, to estimate. Here's one way to break this question down. The number of people that might intentionally try to disseminate a pandemic influenza strain could be estimated as the number of people that know the tools that they would need to do so, times the percentage of such professionals that have the concrete opportunity, let's say based on the lab they are in, times the percentage of people that would be interested in perpetrating such an attack. This is of course simplistic, and the research that actually informs policymakers is far more complex, but we'll use it as our toy example. Now that we've broken this down, suddenly it's much more feasible to estimate. We could get rough proxies for each of these components with information we do have. For example, you need roughly a virology PhD to acquire the tools to synthesize a pandemic influenza strain. Now, of course, there are many lab assistants, immunologists, and others that also have these tools, and many virology PhDs can't actually do this. But it's a good enough approximation for an order of magnitude estimate. We can similarly approximate the other factors with information we know. Note that we've now made some additional assumptions, and one can and should debate whether these assumptions stand up to scrutiny. But if the assumptions are defensible, then we can finally estimate, very roughly, how many people we expect to try and perpetrate this specific attack. Curious about the result? You'll get to complete this estimate yourself in the exercise. Now, we've actually been using Fermi estimation for a while. The ITN framework is an example of Fermi estimation. The original developers of the framework created it to estimate what is the marginal cost effectiveness of opportunities in this cause area. To do so, ITN breaks this hard question down into factors that, though not easy to estimate either, are a bit easier. Another important tool that's useful when a problem is too hard to model, even using Fermi estimation, is deferring to expert opinion. We've already mentioned in Lesson 3 that expert opinion is a legitimate source of evidence when direct experimental evidence is hard to come by. Now, if neither you nor the expert have an explicit model, then the result is guaranteed to be quite subjective. But the intuition of an expert in the field is likely better calibrated than someone without significant experience. Now, you know what's better than asking an expert? Asking many experts. There's also a whole methodological field dedicated to how best to collect and combine expert opinions in a reliable way, called expert elicitation. Some famous methodologies include the Delphi method and Cook's classical model. It's useful to combine information not only when talking to experts, but also when working with other informative but not completely reliable estimates. Combining estimates of any kind can often make your overall assessment better. When you have a few different models or methodologies that give you different forecasts or estimates, their average is often more accurate than each forecast on its own. This is called ensemble forecasting or ensemble averaging. Sometimes there are better ways to combine estimates and averaging. We'll share some resources on that alongside the other tools we mentioned. To conclude, answering questions is harder and more context-dependent when we don't have a wealth of data to draw on. Yet still, sometimes it's no less important. Tools like explicit models, Fermi estimation, expert elicitation, ensemble forecasting, and others can help us do a better job in these circumstances.